assumptions that we made for the Kalman filter. So some things for you to remember is that the Kalman filter is a Bayes filter algorithm, and the crucial assumptions we made was that the state transitions and the measurement models were both linear, right? So the state transition was linear in the sense that xt was a linear function of xt minus 1 and a linear function of ut, right? Likewise, zt was a linear function of xt, right? So these are the linearity assumptions we made. And the second assumption we made was that over these linear models, there was an additive Gaussian noise, right? So we assumed that there was some Gaussian noise added to both the linear transition model as well as the measurement model. And this allowed us to keep the belief distribution as a Gaussian distribution, and that allowed us to localize to a point with some amount of noise around it, right? So this is the assumptions that we made. And I mentioned that we use Kalman filters in practice because these assumptions are often valid and we can get away with it. But sometimes we need to do something more to get the Kalman filter to work. And so in this lecture, we'll look at one such extension to the Kalman filter, right? So here is an example, a very simple example where the linearity assumptions won't hold for us, right? Suppose you have a robot that's moving in a circle, right? It could be moving with a constant velocity, doesn't matter, but the dynamics of the movement is not linear, right? It could be moving at a constant speed, but the dynamics cannot be described in a linear fashion. But one might, think that at any point on the circle, right? Any point on the circle, I might approximate the instantaneous motion of the robot by looking at the tangent to the circle at that point and assuming that the robot is moving on the tangent in a linear fashion. Of course, at every instant, I'll have to keep changing the direction of the tangent, but for that one particular instant on the circle, I can assume that the dynamics are linear for a very short duration. Is that clear? Right? So the whole movement is not linear, but at an instant, I can assume that the motion is approximated by a linear function. Right? So this is the idea behind what we call the extended Kalman filter. So it basically overcomes the linearity assumption by first assuming that the next state probability and the measurement probabilities are governed by some arbitrary nonlinear function. So we're going to assume that xt is a function of both ut and xt minus 1, right? Where g is some arbitrary. Again, as before with the Kalman filter, that is an additive Gaussian noise. So we are still assuming that the noise is Gaussian and it's additive Gaussian noise, but we assume that the main dynamics, instead of being given by a and b, which is like linear multipliers on x and u, I'm just going to assume it's an arbitrary nonlinear function g on xt minus 1 and ut. And similarly for the measurement case, right? Similarly for the measurement model, I'm going to assume that zt is some arbitrary nonlinear function h of xt, and again you have an additive Gaussian noise, which here we denote by delta t, as we did with the Kalman filter. So is that clear? So we have g, which is an arbitrary function that models the next state probability, and h, which is an arbitrary function that models the measurement probability, right? Now what we are going to do next is, just like we did with the circular motion, we are going to try and make a linear approximation for these functions at a specific point on the function. Okay, so it might not be a great approximation for the whole function, but at that point, it's a good approximation of the function, right? So the main reason why we have to do this linearization is as follows. If I have an arbitrary function g and h, right? So if I'm using this, I can still write my update equations. I can still write update equations using g and h. It doesn't look very complicated, but the biggest challenge for me is that the belief distribution, which I start off as a Gaussian distribution. Remember, I start off with mu naught and sigma naught as my the parameters of my belief distribution, and as we keep going around every iteration of the algorithm, right, I just keep updating the mu and sigma because my belief distribution stays a Gaussian. So it makes life a lot easier with the Kalman filter case. But in this case, what happens is we cannot assume that the updated belief distribution would be Gaussian, right? If it's an arbitrary function, it will most certainly not be a Gaussian, right? So one way of getting around this is whatever we described right now, right? So we create a linear approximation, right, for the functions g and h, right? And now once I start using the linear approximation in my updates, right, it just becomes like a Kalman filter, right? It is like applying a Kalman filter, right, but using different functions, right, different linear functions every time I apply it, right, where the different linear functions are obtained by approximating these nonlinear equations. So the actual dynamics of the robot is governed by these nonlinear equations, but when I'm doing the belief updates, I just for a minute think it is linear, so that I can do the same updates or similar updates to what I do with Kalman filters and leave my belief distribution as a Gaussian distribution. Okay, make sense? So the reason we are linearizing this here for doing the updates, the reason we went to nonlinear case because linear assumption was too restrictive for modeling realistic dynamics, and now we are going back to linearization so that I can get my updates to stay Gaussian, right? Updated beliefs to stay Gaussian. So in some sense, I'm trying to get the best of both worlds using what is called as an extended Kalman filter. So there are like numerous extensions to Kalman filter, like hundreds of extensions to Kalman filter. People have different kinds of flavors of Kalman filters, and so each one of these is going to cater to very specific assumptions about the robot, the motion model, the world that you're operating in, and the kind of belief distributions you need, and so on and so forth. And almost all of them have this idea that you're looking at additive Gaussian noise. Okay, that's what makes it a family of Kalman filters. And but then the various other parameters that you would need to model would change, right? So in this course, we're going to look at only the extended Kalman filter because it's a very useful and also simple to understand extension. And you're free to look at other material as you go along. Okay. So let's look at how we are going to do this linearization. So I presume some of you are familiar with what is known as the Taylor series expansion of a function, right? Suppose I have a function g of ut xt minus 1. I can expand it around a point. In this case, I'm expanding it at mu t minus 1, right? I can do that by evaluating the function at mu t minus 1 and keep adding higher powers of the difference. Here I've just approximated it with just the first term, right? So if people remember the Taylor series, so this would be like g prime ut mu t minus 1 into xt minus 1 minus mu t minus 1 plus g double prime ut mu t minus 1 into xt minus 1 minus mu t minus 1 the whole squared, and so on and so forth, right? So that would be the Taylor expansion. But if I just take the first term, so you can see here is a picture of how the Taylor expansion worked like. So that is a trigonometric curve. So it's sine, right? So that's sine theta, right? And then the red line is essentially the Taylor expansion of sine theta around 0, right? With just one term, just the expansion that we show here, right? So this expansion for the theta equal to 0, right? And you can see that it's a straight line because we have linearized it, and it's a pretty decent approximation of the function just around 0, right? It's not quite that. That's a small deviation, but exactly at 0 it's equal, and so that's essentially what we want. We have a linear approximation that is good enough, very close to the point at which we are doing the approximation. So the higher curves, right? So you can see that there is a yellow curve and the orange curve and so on and so forth. These are, as you keep adding more and more terms to the Taylor series expansion, it becomes closer and closer to the full function, right? But we are not interested in that, right? So all we are really interested in is making sure that we have a linear approximation at the point where we want to compute this, right? So coming back, I'm going to use g prime, and I mentioned this is a fairly standard notation. So g prime ut comma xt minus 1 is essentially the partial derivative of g with respect to x, okay, not with respect to u. So it's basically, so it's dou g of ut xt minus 1 divided by dou xt minus 1. So it's basically the derivative with respect to x and not with respect to u, okay. So that's what g prime is. And so we are going to do this approximation, right? So now remember, I said we tried to approximate around a certain point, right? We try to approximate around a certain point. In this picture here, we are approximating sin x or sin theta around theta equal to 0, right? So now I would really like to approximate my g around a point, right, for x, right? So what is the point that I am going to approximate this around, right? So I really need the approximation of the dynamics at t minus 1 so that I can predict what will be the state at time t, correct? So I need an approximation of g at time t minus 1, a linear approximation of g at time t minus 1, so that I can compute what would be the state at time t by using that linear function. I'll take t minus 1, whatever is the state at time t minus 1, I'll compute the state at time t, right? And remember, according to our belief, right, the most likely state at time t minus 1 is mu t minus 1, correct? So the most likely state at time t minus 1, because that's how our belief is determined, right? Remember, belief is a Gaussian distribution with mean mu and variance sigma, right? The belief is a Gaussian distribution with mean mu and variance sigma. So the most likely state under the belief is going to be the mean, right? So for the belief at time t minus 1, the most likely state is going to be mu t minus 1, right? So I'll take the most likely state, which is mu t minus 1, and I'll do a linear approximation at that point. So what it really means is I will evaluate the Taylor series at mu t minus 1, but I'll use only the first term here, okay? So my approximation for g of ut comma xt minus 1, this approximation is good at mu t minus 1 is equal to g of ut comma mu t minus 1. Remember that now this quantity, right? So this quantity, right? So this quantity is a constant because I know what ut is. Ut is no longer a function now. I know what ut is. I have already applied ut, right? And mu t minus 1 is again a specific value for xt minus 1, right? That is what I think is the most likely state. So it's no longer variable. It's actually an assignment to xt minus 1. And what you should remember, even though g is a function of u and x both, but in this particular instant, when I'm applying my model g, I've already picked my ut, right? I'm not using g to pick ut, already picked my ut. So ut is a constant because it's already given to me when I'm doing my belief updates, and mu t minus 1 is a constant that comes from my previous belief, right? So now that I have plugged in specific values for x and u, right, I can actually compute what g is at this point. So this is actually a specific quantity, right? It's no longer a function. So this is basically some quantity that is in the x space, right? That's in the state space. It's a specific state. It's no longer a function, okay? And then what I'm doing here is, this is the first term in the Taylor series expansion. So I'm going to take the derivative of g with respect to x, right? And then I'll multiply that with the difference of xt minus 1 minus mu t minus 1. So this is the part that gives me the functional form, right? So it's a functional form in terms of xt minus 1, right? And so notice that I'm using a specific notation here. So I use g prime of ut comma mu t minus 1. What it really means is that I take the derivative, I compute this derivative, right? And I substitute mu t minus 1 for xt minus 1 here, and I compute the value of the gradient at that point. So this also is a constant, right? So that also is a constant, right? So now I converted my my nonlinear function g ut xt minus 1 to some kind of a constant plus g prime, which is a constant, times xt minus 1 minus mu t minus 1, which is a constant. So basically I've converted that into some kind of a equation which is linear in xt minus 1. Okay, so all the higher order powers of xt minus 1 that could have been there in this have vanished, right? Because of the Taylor series approximation. Remember that this is actually an approximation, right? And it is good to go at mu t minus 1 for a very, very short interval, right? Not throughout the function. Okay, I hope that is clear what we are doing with the linear approximation. So now that we have this approximation, we can go ahead and try to start writing our update equations, right? So I'm going to assign capital GT, right, to be equal to G prime ut comma xt minus 1. So that's basically a matrix of size n cross n, because I'm going to take the partial derivative with respect to all the components of x, right? So n is the size of x, right? And so G prime of ut comma xt minus 1, right? Now I can rewrite my G, which is what we did in the previous slide. I'm just writing it using my GT notation. I'm going to rewrite my G of ut comma xt minus 1 is equal to, or approximately equal to, G of ut comma mu t minus 1, and as we saw that this was a specific evaluation of the function G, plus GT, which is the Jacobian, times xt minus 1 minus mu t minus 1. So I mean, I presume all of you are familiar with the Jacobian. You must have seen it multiple times already in the course, right? And so this is essentially the Jacobian times xt minus 1 minus ut minus 1, right? So the next state probability, which is what is our motion model, which is probability of xt given ut comma xt minus 1, can be approximated as follows: as a Gaussian distribution. Remember that our next state distribution was given by, right, our next state xt was given by G of ut xt minus 1 plus a Gaussian noise epsilon t, right? And if you remember from our previous lecture, so epsilon t is a Gaussian with zero mean and covariance matrix RT, right? So that's essentially the same thing that we're using here, right? And therefore, so since it has a zero mean, so I'll be basically adding this value to it. So that's the mean. So it is the next state probability distribution is basically a Gaussian with the mean given by G of ut comma mu t minus 1 plus gt times xt minus 1 minus mu t minus 1. So that is essentially the mean of the Gaussian for the next state distribution, and the covariance is RT as we had earlier, right? So I hope that is clear. Now that we have the state transition model, we had something similar like this, right? So what did we have for the Kalman filter? So we had A plus, right? So we had A xt minus 1 plus B ut, that was the mean, and the covariance was RT, right? Similarly, we can approximate the observation function h of xt as h of mu t bar. Why are we getting a mu t bar here? Why not mu t? We used mu t when we did the next state probability, but we are using mu t bar here. So why is that? So you should remember that we use the observation function, or we use the measurement function only with bell bar, not with bell, right? So when I come to bell bar, I have already updated my most likely location from mu t minus 1 to mu t bar, right? So I will be doing the linearization of my h at mu t bar, because that is where I actually end up using h. I use it with updating from bell bar to bell, right? Bell bar of xt to bell of xt. So that is what I am using it for, and therefore we will use mu t bar as the point around which I will linearize the function. Okay. So h of xt, I am approximating this by h of mu t bar plus h prime of mu t bar. H prime is, as you can see, is a partial derivative of h with respect to x, times xt minus mu t bar. This is exactly like the Taylor expansion that we used for G, except that it's around mu t bar. Okay, and likewise, just like we did earlier of writing gt as, I mean g prime as gt, similarly we write h prime as capital ht, and this is the partial derivative for the measurement function, right? So I'm approximating h of xt as h of mu t bar plus capital ht times xt minus mu t bar. Okay, so that's my function. And now remember, so you have to use mu t bar here because that is the most likely state at the time when I actually use my h. Okay, so now my measurement probability, which is probability of zt given xt, right? The probability of zt given xt can be approximated as a normal distribution with mean given by h of mu t bar plus capital HT times xt minus mu t bar, and qt, which is a covariance of the noise term delta t. Remember, delta t is a Gaussian noise, additive Gaussian noise with mean 0 and covariance qt, right. So now I'll do the same thing here, but the mean, now the new mean, instead of being ct times xt as we had earlier, right, it's going to be h of mu t bar plus ht times xt minus mu t bar, and qt would be the covariance as before. Okay, so that's, so you can say that it's almost like the Kalman filter, except that instead of using ABC, you're going to use the ht and gt, which is essentially helping us linearize the function. Okay, now once we have these linearized versions of the filter, right, of the motion model, and we basically rewrite the extended Kalman filter algorithm to look very much like the original Kalman filter algorithm. Again, lines 2 and 3, right, or the update equations for go from bell xt minus 1 to bell bar xt, right. So as before, your bell xt is given by mu t minus 1, bell xt minus 1 is given by mu t minus 1 and sigma t minus 1. I have the action ut, I have the observations at t. Now I can use that to compute my new bell bar of xt, which is again obtained by computing mu t bar and sigma t bar, and this expression looks very similar to what we had earlier, except that instead of a, b and thing, so we are just using g now, right. And likewise, we have the and so one thing to note is that I'm actually using the exact g here, right, g of ut comma mu t minus 1. So I'm basically looking at plugging in mu t minus 1 and computing what mu t bar is, right. So that's something to note, right. And then again, I have the Kalman gain, which is computed in a similar fashion, and I have lines 5 and 6 now compute bell of xt from bell bar, and likewise very similar computation to what we had earlier in the Kalman filter. So this is essentially the extended Kalman filter algorithm. So it is more powerful than the Kalman filter in the sense that it uses a nonlinear model for both the movement as well as the measurement, but it retains the same convenience of Kalman filter because I can assume that the belief is Gaussian and it will stay Gaussian through my updates. Okay, so that's basically the extended Kalman filter. So we can stop here.